in this video, we're going to take a look at the E2 reaction, which is our bimolecular or concerted elimination reaction. So in this reaction, our base is what starts the reaction. And so our base is going to form a bond with the beta hydrogen. The electrons from the carbon-hydrogen bond are going to shift in to form the pi bond, and the leaving group will be pushed off the molecule. In order for all of this to take place in one step, it's necessary that this hydrogen and the leaving group that's being eliminated are in a specific orientation. Specifically, they need to be in the same plane, and they need to be pointing in opposite directions, which we call anti-coplanar. This required orientation, we will see, has effects on the stereochemistry of the product, and that's what we're going to focus on in this video. So the first thing that we're going to consider is the case of a stereoselective E2 reaction. So a stereoselective reaction is a reaction in which more than one possible isomer or stereoisomer of the product can be formed, but only one of those stereoisomers would be formed as the major product due to its thermodynamic stability. So if we take a look at this secondary alkyl halide that I have drawn here, I've highlighted two different beta hydrogens, one in blue and one in red. So from this current orientation, only the hydrogen that's highlighted in blue is able to be eliminated in an E2 reaction because that is the hydrogen that is currently 180 degrees away from the leaving group. So if we were to do the E2 reaction from this conformation, what we would see in the alkene product is that this orientation of the alkyl chain would be preserved in the product. So we would see that the methyl group would be pointing down from the alkene carbon, and the ethyl group would be pointing up. So let's go ahead and show that reaction just using a generic base. So I'm just going to take my base, and if it abstracts that blue hydrogen, these electrons should flow in to form the alkene, and the bromine will be kicked off. And what we will see is, again, that this stereochemistry, the orientation of that alkyl chain, will be reflected in the alkene product. So our product will look like this, which is the transalkene. If we wanted to show the elimination of the hydrogen in red, what we would have to do is we would have to convert this molecule into an orientation that had that hydrogen and this bromine 180 degrees away from each other. Now that can happen because, as we know, a carbon-carbon single bond can spin. So what we would want to consider is that we'd just be spinning a carbon-carbon single bond to move a group where we need it to be. So what I'm going to do, I'm going to choose to spin this carbon-carbon bond to move my bromine onto that dashed line where the hydrogen is, which when I spin that hydrogen, it would bring it up to where the ethyl group currently is, and this ethyl group would shift down to where the bromine currently is. So let me go ahead and draw the product of that bond rotation. Still going to keep my hydrogens highlighted, one in blue and one in red, so that we can keep track of which beta hydrogen we're eliminating. Okay? And when I follow down to this center, I'll see that I brought this ethyl group down onto a wedge. So there it is. I brought the bromine over to where the hydrogen is. So there that is. And I brought that hydrogen up where the ethyl group was. And now if I do my E2 elimination, I'm set up so that this red hydrogen and the bromine are now 180 degrees apart. So my base can now abstract this red hydrogen, pushing the electrons in to form the pi bond and pushing off the bromine. So when I draw the reaction, now I see that my methyl group and my ethyl group are both pointing down, formation of the cis alkene. From what we know already about the thermodynamic stability of alkenes, we would expect that we would form this trans alkene as the major product. Because we have two possible stereoisomers that can form trans and cis, but one is formed preferentially as the major product, we say that this is a stereoselective reaction. So what I want to consider now is an E2 reaction that is stereospecific. Now for a lot of students, this is probably the most difficult thing to predict in E2 chemistry. So a stereospecific reaction is a reaction in which the stereochemical outcome of your reaction is dependent on what stereoisomer of the starting material that you're using. So we have two different stereoisomers of the same secondary alkyl halide. So in our first molecule, we only have one carbon atom that has a beta hydrogen, and it's this one right here. So I'm going to go ahead and draw in that beta hydrogen. I see that I have a methyl group that's pointing out at me, so that means the hydrogen at that same position is pointing into the plane of the board, or we can represent that on the dashed line. This is the only beta hydrogen, so it's the only one that can be eliminated from this molecule. So the reactive conformation will be one where that hydrogen and this bromine are 180 degrees apart. And what we can see is that they are currently already 180 degrees apart. We have that hydrogen on a dashed line and the bromine is on a wedge line. So we can go ahead and do this E2 elimination reaction. I've got sodium methoxide as my base, so I'm going to go ahead and draw the methoxide ion. And I can show that methoxide abstracting this blue hydrogen, these electrons swinging in to form my alkene, and pushing off the leaving group. So what we'll see is that this orientation of our alkyl chain will be conserved in that alkene product. So I will only have one product formed from this reaction. It'll be one with this phenyl group pointing out, the methyl group pointing down, and that terbutyl group also pointing down. That would be the only product of this reaction. So what we found is this stereoisomer of our starting material specifically gives us this alkene product. If we look at the opposite stereoisomer, so again we have only one beta carbon that has a hydrogen, it's this one here. This time though, if we draw that hydrogen in, we'll see that it's going to be sticking out of the plane of the board because this methyl group is pointing back. So let me go ahead and draw that in. From this current orientation, that hydrogen and this bromine are not 180 degrees apart. We need to do a bond rotation about this carbon-carbon single bond in order to see the major product. So I'm going to rotate on this side of the molecule. So let me go ahead and draw in the fourth bond that's on this carbon, that's to a hydrogen. And that hydrogen is facing away. So ideally, I would like this bromine to be in the position where that hydrogen is, so I'm going to spin around this bond. So I'm going to spin so this bromine slides over to where the hydrogen was. That hydrogen shifts down to where the terbutyl group was, and this terbutyl group is going to swing up to where that bromine was. So let's draw the product of that bond rotation, and then we can do the E2 reaction. dashed line. And finally, the hydrogen atom has shifted down where the terbial group was. And so if I do the elimination from this conformation, now I've got the hydrogen and the bromine where they need to be 180 degrees apart, so I can draw my base. So there's the methoxide base. I'm going to extract this hydrogen. The electrons from the carbon-hydrogen bond are going to shift in to form a pi bond, and the bromine will be kicked off. And what we'll see here is now that we changed the stereochemistry at this center, it gives us the opposite alkene stereoisomer as a product. So this time in the product, I see that my phenyl ring and my terbial group are on the same face of the alkene. This methyl and hydrogen are on the same face of the alkene, which is the opposite alkene stereoisomer that we got in the first reaction. And this again would be the only product of the reaction. Reactions like this, where the stereoisomer of your starting material determines which stereoisomer of the alkene product you get, are stereospecific reactions.